omega. Actually, here we are changing the variable, that's all. Use, and finally you will get this as function, and we are denoting it as f bar omega. Okay. So the corresponding inverse Fourier transform of this one is f bar omega equal to 1 over 2 pi minus infinity to plus infinity f bar omega e to the power minus I omega x. Okay. So this is first one. This is we call it as the Fourier transform, Fourier complex transform. This is our first one. Okay. So first one. So look at the things. Both ranges up minus infinity to plus infinity. Here also it is minus infinity to plus infinity. So this is called the Fourier transform, or we can call it as the Fourier complex transform. So here the interval range of the domain should be minus infinity to plus infinity. Second situation, we have a function fx which is defined from 0 to infinity. The range is 0 to infinity. Then we have two types of transformation. One is Fourier sine transform. Fourier sine transform is denoted by fs fx is equal to 0 to infinity. Look at here. Complex transform minus infinity to plus infinity. This one is 0 to infinity. fu sine omega u into, and we denote it by f bar s. Actually, this s denotes sine transform, Fourier sine transform. Similarly, the inverse Fourier sine transform, fs inverse of the function here, it is equal to 2 over 5 integration 0 to infinity fs bar omega sine omega x so this is Fourier sine transform. Here the range should be 0 to infinity. The second one, Fourier cosine transform. Here function need not to be, in these cases function need not to be odd or even function. It can be applied to any type of function. Okay. In the Fourier complex transform, sorry, Fourier cosine transform of the function fx is denoted by here also 0 to infinity. F bar, sorry, fu cos omega u into. Okay, so we denote it by f bar c. This c stands for cosine transform. Sorry. Function, finally you will get the function in terms of omega. Similarly, its inverse transform equal to 2 over pi. Here look at the coefficient. In complex transform it is 1 over 2 pi. In sine transform it is 2 over pi. Here also it is 2 over pi. 0 to infinity. F bar c omega cos omega x into. Okay, so these 6 formula Fourier transform, this is called the Fourier complex transform, and its corresponding inverse Fourier transform When the function is defined in this range, we can find two types of transformation. One is the Fourier sine transform. The other one is the Fourier complex transform. Sorry, Fourier cosine transform. Right? So this one we are familiar with. The second thing is now actually the application we are talking here is solving partial differential equation. So partial differential equation, basically we know that it's a function of two variables. The unknown function ux comma y. Okay, this is the unknown function. This is the unknown function. We want to find out this function by solving the partial differential equation. Okay. This is the unknown function. By solving a partial differential equation, unknown function, we want to find the unknown function. Sorry. Now here we have two variables. Here we have two variables. One is x there and the other one is y. So when you take the Fourier transform, actually we can take the Fourier transform with respect to one variable only. So here we are taking our Fourier transform variable as x. We take x as our Fourier transform variable. Okay. So Fourier transform of this function, when you talk about the Fourier transform of this function ux comma y, which is equal to Fourier transform. Okay. Fourier transform of this function. So let me write it again. So Fourier transform of the function, please carefully understand these things. Ux comma y, we denote it by u bar omega comma y. So we keep y as it is. There's no change in y. Okay, there's no change in y. We only do changes in x because x is the primary variable. So we are taking the Fourier transform with respect to x. Then in the place of x, we get omega, and here the function is u. Therefore, we get the Fourier transform of u as u bar. Now, we have some questions about this one. Say, what is the Fourier transform of, if the Fourier transform of u x comma y equal to u bar omega y? Okay, so we'll write if Fourier transform of u x comma y equal to u bar omega y, what is the Fourier transform of da by u over da by x? We have a question. What is the Fourier transform of? What is the Fourier transform of? What is the Fourier transform of da by u over da by x? So then this is equal to, okay, then this is equal to, we are going to use the definition, minus infinity to plus infinity, minus infinity to plus infinity. Our function this time is da by u over da by x into e to the power I omega x. So actually here we are putting, you see, here we are putting u. Here we are putting u because we are changing the function u. So if you want, you can change it as lambda or something, because you want, you can just put lambda. Okay, no problem. Lambda into b lambda, because already we are taking the function as u, no. Therefore, I am taking x as lambda. Okay, so then this is equal to what? So using the integration by parts method, okay, keep the first function as it is. Okay, so I'm taking this as my first function and this as my second function. So first function into integration of this function. So that means that e to the power I omega lambda into integration of this one. So what is the integration of this one? Here, yeah, actually we have to take this with respect to lambda. Okay, so here the function is with respect to lambda. So integration of this one is what? integration of this one is u minus infinity to plus infinity minus, okay, integration, differentiation of this function. Differentiation of this function is I omega e to the power I omega lambda into, here the range is minus infinity to plus infinity. Range is minus infinity to plus infinity into this function u into d lambda. Okay, so with the assumption that u tends to 0. Okay, we'll write it here properly. So we can say that say this is equal to 0. This one we are taking as 0. I'm saying y 0 minus integration. So I'm taking I omega out. So that becomes look at here, minus I omega integration minus infinity to plus infinity. Okay, minus infinity to plus infinity u into e to the power I omega lambda into d lambda. So what is this? This one is nothing. Okay, Fourier transform of u. This one is nothing, Fourier transform of u. Therefore, this is equal to minus I omega u bar omega comma y. Okay, so here we are doing a small assumption, that is we are taking, assume u tends to 0 as lambda tends to plus or minus infinity. So why we are putting 0 here? We are taking this assumption. What is the assumption here? As lambda tends to plus or minus infinity, u tends to 0. Therefore, this part becomes 0 and we are getting this part. Okay, so da bar u over da by x, is equal to, okay, Fourier transform of da by, carefully understand, Fourier transform of da by u over da by x is equal to minus infinity to plus infinity, da by u over da by lambda. I'm changing x by lambda. I'm changing by x by lambda. That's all. Okay, I'm just changing the variable. That's it. Okay, da by u over da by lambda e to the power minus I omega lambda d lambda. Then I am integrating this one with respect to lambda. Okay, so then I am taking this as my first function and this as my second function. So first function into integration of the second function. So if you integrate this function with respect to lambda, okay, then that becomes u. Okay, that is, the range is minus infinity to plus infinity minus infinity to plus infinity, and the differentiation of this function. So what is the differentiation of this function? I omega e to the power I omega lambda into, again, integration of this function, that becomes this one. But here this part becomes 0 as our assumption. Therefore, and I'm taking I omega out, then this becomes minus I omega minus infinity to plus infinity u e to the power I omega lambda into d lambda. But here we are saying that actually from the definition of Fourier transform, this is nothing, Fourier transform of the function u. Therefore, the first derivative with respect to x, Fourier transform of first derivative with respect to x, you can write it as minus I omega u bar omega y. Similarly, we can find out the second derivative, Fourier transform of the function da by u over da by x squared. Okay, look at here. The variable we are using is x. Therefore, this is equal to minus infinity to plus infinity. I'm changing the variable, just changing the variable. So if you want, you can keep the same variable, no problem. So I'm putting it as da bar squared u over da bar lambda squared into e to the power I omega lambda into d lambda. Okay, so this is equal to actually. This is equal to, I am taking this as my first function and this as my second function. So integration of the first function. So if you integrate this function once, you will get da bar u over da bar lambda into first function, that is e to the power I omega lambda. The range is minus infinity to plus infinity. Okay, minus infinity to plus infinity minus integration of, again, integration of this function, that is da bar u over da bar lambda into integration of this function, differentiation of this function is what? I omega into e to the power I omega lambda into d lambda. Range is minus infinity to plus infinity. Okay, so this is equal to, look at here, we are again assuming da bar u over da bar lambda tends to 0. We are assuming da bar u over da bar lambda tends to 0 as lambda tends to plus or minus infinity. As lambda tends to plus or minus infinity. As lambda tends to plus or minus infinity. So then this part vanishes. Therefore, that is equal to, okay, that is equal to 0 minus, okay, let me take I omega out. So I omega into integration minus infinity to plus infinity da bar u over da bar lambda into e to the power I omega lambda into d lambda. Okay, so actually you can differentiate once more, or otherwise you can use the result of this one, da bar u over da bar x. What is that? Minus I omega u bar omega. So if you just put that one, so minus I omega into again, what is that? Minus I omega u bar omega. So minus I omega into u bar omega comma y. So that becomes what? Minus minus out. We get I squared omega squared u bar omega y. Okay, so I squared means this is equal to what? Minus omega squared u bar omega y. Okay, so this is how. So similarly, you can consider any partial derivative. Da bar n. You should know this proof, huh? We may ask this proof in the examination. Da bar n over da bar n da bar u over da bar xn. Look at the variable. This is equal to, we have already studied, minus I omega to the power n into u bar omega 1. But this is true. This is true with some assumption. Look at here. Look at the assumption. Here we are taking u tends to 0. Here we are taking da bar u over da bar lambda tends to 0. Therefore, already here we are using this result also. Therefore, this is true. This is true what? Under the condition. Which condition? Assumption. With the assumption. Okay. With the assumptions. Okay. U comma da bar u over da bar x comma da bar u over da bar squared u over da bar x squared dot da bar n minus 1 over da bar x to the power n minus 1 u. All tends to 0 as x tends to plus or minus infinity. So under this condition only, we can use this formula. Under this condition, under this assumption only, we can use this formula. Okay, so you have to clearly understand that one. Under this assumption, without this assumption, actually you can't do anything. Without this assumption, you can't do anything. Okay, so this is actually for Fourier transform of derivative with respect to the variable x. Similarly, okay, so we can have the Fourier transform of da bar n. Okay, look at here. Fourier transform of the function da bar n u over da bar yn. Look at the variable. Now the variable is yn. So in this case, actually you can write it as integration minus definition. Integration minus infinity to plus infinity. Okay, da bar n u over da bar yn e to the power I omega lambda into d lambda. Because our transform variable is x, but here we are having the derivative with respect to y. So you can write this as, look at here carefully. Now here actually integration is with respect to lambda. Here the derivative is with respect to y. So what you can do is you can take this y out. You can take this derivative out. That means that you can write this as d over dy. Sorry. You can take this derivative operator out. I'm writing here. This is equal to dn over dyn minus infinity to plus infinity. Okay, minus infinity to plus infinity. U into e to the power I omega lambda into d lambda. Okay, so this is nothing but, this part is nothing but u bar. Therefore, dn u bar omega y over dy. Okay, so this is simple. Here there is no any assumption. Because here actually the y is secondary. We are taking y as our secondary variable. So when you consider the derivative of a function u, Fourier transform of the function of derivative with respect to y, then actually you can take the derivative operator out. But here you can't do that one. Here actually you can't do that one because the variable is lambda. Here the variable is the primary variable. Here the variable is secondary variable. Therefore you can take it out. Therefore any power you can take, just write it in this form. But if it is with respect to x, then actually you have to use this formula. Remember that this formula is also under the assumption that u da by u over da by x, da by square u over da by x, all tends to 0 as x tends to plus or minus infinity. Do you understand up to now, students? Hello, do you understand?
Yes, sir.
Okay. What about others? Others also understand? Hello? Definitely, you must know this proof. Huh? You must know this proof. I will ask in the examination. Okay. Actually I am using just definition of Fourier transform. Okay. Similarly, what you can do is Fourier transform of now we'll say if Fourier transform, sine transform of the function fx is ux comma y equal to say u bar s omega y. Okay, omega y. U bar omega. Now I am asking, what is the sine Fourier transform of da bar u over da bar x? Now we are going to use the definition. So what is the definition says? 0 to infinity. Remember, 0 to infinity. Here, da bar u over, I'm changing the variable because earlier we are changing normally into u, no? Since here u is the function, I'm just changing as lambda. Da bar u over da bar lambda into sine omega lambda into d lambda. Okay? Into d lambda. So this is equal to so now I'm going to take this as my first function. Sorry, I'm going to take this as my first function. So that becomes integration of this function. So that is that becomes what? U into U into sine. Yeah, there's omega. Yeah, sine omega lambda. Sine omega lambda. I want to put 0 to infinity minus integration. So U into differentiation of this one. So differentiation of this one is omega cos omega lambda into d lambda. Now, similarly, we are using the assumption as lambda tends to infinity 0, or when lambda tends to 0, this function becomes 0. Okay, so this is equal to 0. This is equal to 0, and yeah. And yes, of course, this is 0 to infinity, no? 0 to infinity. We are taking this as our first function. Of course, 2 delta 2 by u over da by this. So this one tends to 0, and this is right. Okay, this one is 0 because we are assuming that u tends to 0 as lambda tends to 0. Okay, minus omega is out here. We can take omega out, 0 to infinity u into cos omega lambda into d lambda. Okay, now this is what actually. Now, what shall we do now? Yeah. So how to short this out now? How to find the derivative of this one? You can put it like minus omega. Okay, minus omega. Okay. Okay, let's talk about the second derivative. So that's fine. No, second derivative. We'll talk about the second derivative. I'm sorry. We'll talk about the second derivative. Okay, we frequently want the second derivative now. So we'll have the second derivative. Sorry. First derivative is also okay. First derivative is okay, but actually we want the second derivative. We want the second derivative. Therefore, we'll we'll consider the second derivative. Okay. I'm sorry for that. We'll consider the second derivative. Huh? So if you take the second derivative, this becomes, okay, so let me take this as my first function, but this one as a first function, therefore that will I will get it as a sine lambda u into integration of this one, that becomes first integrate da bar u over da bar lambda. The range is 0 to infinity minus integration 0 to infinity, and the derivative of this one is da bar u over da bar lambda, and differentiation of this one is omega into cos omega lambda into d lambda. Okay, I'm considering the second derivative. So as we assumed, this part tends to 0. This tends to 0 because we know that sine omega lambda tends to 0 as lambda tends to 0. An assumption is that da bar u over da bar lambda tends to 0 as lambda tends to 0. So with that one, this part becomes 0. Therefore, finally, this one boils down to minus omega is also here. There is omega here, so I am taking the omega also out. So I am taking the omega also out. So minus omega 0 to infinity. Look at here, 0 to infinity, and 0 to infinity da bar u over da bar lambda cos omega lambda into d lambda. Let me write it clearly. So da bar u over da bar lambda into cos omega lambda into d lambda. This proof is not in your handout. That is why I'm doing it here. So this is equal to, again I'm integrating minus omega into, okay, minus omega into, I'm integrating this one, so that becomes u over u into, and this one I get cos omega lambda minus, so I want to substitute the values, 0 to infinity, 0 to infinity. Actually, the variable lambda is 0 to infinity. Okay, 0 to infinity minus integration 0 to infinity. Derivative of the integration of this one is u into integration of this one, derivative of this one is minus, so that becomes plus. No? So this becomes plus omega sine omega lambda into d lambda. Okay, d lambda. Now we assume that, so there is a plus here because, let me write it minus, and this is minus sine lambda. Then you can take minus omega out. So minus omega, and here look at here, as lambda tends to infinity, look at here. As lambda tends to infinity, we say that u tends to 0. As lambda tends to 0, okay, what will happen? This becomes what? Sorry. sorry, this becomes what? U 0 comma y, because lambda mean our variable is actually omega, no? So that becomes 0, because here this part becomes 0, this part becomes 1, because when you put lambda equal 1 here, this actually this becomes this part. So let me substitute and show you better. So this is equal to minus omega into, as lambda tends to infinity, this is 0, this part is 0, therefore 0 minus, okay, as lambda tends to 0, okay, this one is 1, and this becomes u 0 comma y, okay, minus, there is minus here, and I am taking minus omega out, so this becomes plus omega squared 0 to infinity u into sine omega lambda. Okay, so now when you multiply this one, minus into minus is plus omega u 0 comma y, okay, u 0 comma y, I'm sorry, this one is omega, not omega square, omega, no, I'm sorry. And when you multiply this one, we get minus omega square, and this is what? This is actually nothing, sine transform of function u. So this is u bar s omega comma y. Okay, so actually here also we are having the assumption this one, as lambda tends to 0, sorry, not as lambda tends to 0, yeah, as lambda tends to infinity, u tends to 0, as lambda tends to infinity, u tends to 0. Right. So that is the formula. So look at here, Fourier sine transform of the function u x comma y, not the Fourier sine transform, second derivative, da bar squared u over da bar x squared, that is equal to omega u 0 comma y minus omega squared u bar s. Okay, that is the formula. This is also assumption is there. What are the assumption we have? U comma da bar u over da bar x tends to 0, as lambda tends to plus or minus infinity. Under this assumption only we can use this one. Similarly, we can find the Fourier cosine transform. Say Fourier cosine transform of ux comma y equal to, if we say u bar c omega y, then we consider Fourier cosine transform of the second derivative with respect to x. And that is equal to, according to the definition, we have 0 to infinity u, sorry, we have da bar squared u over da bar x squared into da bar lambda squared da bar lambda squared into e to the power, not the e to the power, cos transform, cos omega lambda e lambda. So using the method of integration by parts, you can write it as da bar u over da bar lambda into cos omega lambda minus infinity to, sorry, 0 to infinity, minus integration 0 to infinity, da by u over da by lambda, and integrate differentiation of this one is minus omega sine omega lambda into d lambda. Okay, so as earlier, what you can say, you can write this as, okay, look at here, da by u over da by lambda. Here as lambda tends to infinity, as lambda tends to infinity, okay, we assume da by u over da by lambda tends to 0. So that part becomes 0 minus, okay, as lambda tends to 0, this one, da by u over, you can put da by x, okay, da by u over da by x as x tends to 0. Okay, because as lambda tends to infinity, this becomes 0. As lambda tends to 0, actually cos lambda is 1. Therefore, this becomes da by u over da by x when x equals 0 minus, you can take minus omega out. So that becomes plus omega 0 to infinity plus omega 0 to infinity. And then da by u over da by lambda sine omega lambda. Sine omega lambda. So this is equal to, look at here, this becomes a minus da by u over da by x as x tends to 0 plus omega into integration of this one is, we know that u into this one, we know that u into sine omega lambda, where 0 to infinity minus integration 0 to infinity u omega cos omega lambda into d lambda. Okay, so this is equal to minus da by u over da by x as x equals 0 plus w. Here actually look at, as lambda tends to 0, u tends to 0. As lambda tends to 0, sine omega tends to 0. So ultimately this part becomes 0 because 0 minus, here you can take omega out. So then minus omega integration 0 to infinity u into cos omega lambda d lambda. Okay. So this is equal to minus da by u over da by x as x equals 0 plus, so the plus omega and minus omega is here, therefore minus omega squared, and this is nothing but u bar c omega y. Okay, so this is also with the assumption u comma da by u over da by x tends to 0 as x tends to 0. So this is the formula. Okay, this is the formula. So that is the formula given here. Look at here. Now look at here. Look at the proof. Here proof is not given. Actually, Fourier transform of this one, we got this one, minus omega squared u bar omega y. We got this one. We proved this one. The proof is given here. For this one, proofs are not here, just we had the proof. Fourier transform of sine Fourier transform of second derivative is omega into u0y minus omega squared u bar omega y. Fourier cosine transform, that is minus da by u over da by x equals 0 minus omega squared this one. Okay, so these three things you must know. The proof also you must know. Here I have given the proof. Here I have the proof. All these are under the condition this one. Look at the condition. U da by u over da by x all tends to 0 as x tends to plus or minus infinity. Another thing, actually here I put lambda. If you don't like to put lambda, you can keep x as it is, no problem. You can have it x, no problem. Okay. So in this proof, you can have, instead of putting lambda, you can put x as it is. Okay, no problem. Okay. So those three things you must know this one. Okay. So let me write it again. Quickly summary. Let me write the summary. Summary. The first one is this one. Fourier transform of da bar squared u over da by x squared. That is equal to minus omega squared u bar. Second one, Fourier sine transform of da bar squared u over da by x squared. That is equal to u. Sorry, that is equal to what? Omega u, no? Omega should come. Omega u 0 comma y minus omega squared u bar. Third one, Fourier cosine transform of second derivative, all with respect to x. That is equal to minus da by u over da by x equals 0 minus omega square u bar. Okay, so these all are second derivative. So in addition to this one, Fourier transform of da bar n u over da by xn. Okay, so you can have the proof, that is minus I omega to the power n. Actually, from this one, you can have this one. Okay, you can have this one. For this one, we are not getting the nth derivative because nth derivative will be lengthy. Okay, nth derivative will be lengthy. All these things are with the assumption u da by u over da by x, comma da by u over da by x squared. Sorry, da by x squared u over up to da bar n minus 1 u over da bar x n minus 1 all tends to 0 as x tends to plus or minus infinity. With this assumption only, you can use this formula. Okay, look at here. All these are with respect to the variable x, with respect to the variable x, with respect to the variable x, with respect to the variable x. Similarly, if it is with respect to the second variable, that is Fourier transform of da bar squared u over da bar y squared, then this is nothing, okay, d squared u bar over dy squared. Fourier transform of sine Fourier transform of da bar squared u over da bar y squared. This is nothing, d squared u bar s over dy square. Fourier cosine transform of second derivative. This is nothing but da bar squared c bar over dy square. So if it is the second variable y, then it is just this way. If it is with respect to x, and this is this way. Do you understand this one? Right. One more thing before we move to the handout. One more thing. Now, when you have a second derivative differential equation, second order ODE, look at carefully. Second order AD. Now, the auxiliary equation has the solution. The auxiliary equation has the solution, complex solution. First one, alpha plus I beta, comma alpha minus I beta. Second order, huh? We are talking about the second order, therefore definitely there will be two equations. What is the solution? Complementary function is what? Yx is equal to, can anybody tell me if this is the solution? Alpha plus I beta, alpha minus I beta. Two complex solutions, conjugate pairs. What is the solution? Can anybody tell me what is the solution? What is the solution? Quickly, we are running out of time. We want to finish the handout today. Second order equation. What is the solution if the auxiliary function has these two solutions? Alpha plus I beta, alpha minus I beta form. So what is the complementary function? What is the complementary function if the auxiliary equation has alpha plus I beta, alpha minus I beta solutions? X equal alpha plus I beta, x equal alpha minus I beta. Yeah. So then that becomes e to the power alpha x into a cos beta x plus b sine beta x. Please write this one, huh? Because some of you have forgotten last time when I asked this one. Now, when you have two distinct solutions, K1, comma K2, two real distinct solutions, real distinct, distinct means different. Then what is the complementary function? Yx equal what? Please tell me quickly. Yes. So you can write it as a e to the power k1x plus b e to the power k2x. Now, this one, okay, actually can be written as this one with some situations, okay, with some conditions. You can write it this as this way also. A cos k1x plus b sinh okay. So here, this one, in this way also it can be written. So if you let, not this way actually, not this way, you can write this way, I'm sorry. Yeah, let me put A. Then another constant C and D. Another constant C and D. Where if you put C equal A plus B by 2, or if you put yeah, if you take C equal A plus B by 2 and D equal not this way, I'm sorry, if you put like this, I'm sorry. If you put A equal C plus D by 2, comma B equal C minus B by 2, you can write it in this way, where first x is equal to e to the power x plus e to the power minus x divided by 2. These are called the hyperbolic functions. So we studied in MATLAB also. First is e to the power x plus e to the power minus x divided by 2. Since x, these are the definitions. Cos x is equal to e to the power x plus e to the power minus x divided by 2. Sin x, you can write it as e to the power x minus e to the power minus x divided by 2. There are some similar to trigonometric identities, okay? But we have this one. Cos squared x minus sin squared x equal to 1. In trigonometry, we have actually cos squared theta plus sin squared theta equal 1. No? Here, it is not the case. Cos squared x minus sin squared x is equal to 1. Okay. So please verify this one. And there are some trigonometric identity also. So using that one, using the things, you can write this one. Okay. So because in the second question, actually, we had similar to this one. So that is why I wanted to talk this one. Okay. Right. Third one, if you have auxiliary equation K1 equal K2 equal K. That means that real same. Then what is the auxiliary function, complementary function? Can anybody tell me? Real but same. What is the complementary solution? Yes. So that is equal to A plus bx into e to the power kx. Okay. So these three things you must know. These three things you must know. Actually, you can write this one under some conditions. Okay. If you let this a equals c plus d by 2 and b equals c minus d, actually you can write this in the form of hyperbolic function. Okay. Hyperbolic function. Okay. So just try to understand these three things. Another thing, first order ODE. First order ODE. So if you have a function like this, dy over dx plus px y equal qx, then what is the solution of this equation? What is the integrating factor? Can anybody tell me what is the integrating factor of this equation? E to the power integration px into dx, dx into dx. Okay, so then you can easily solve this equation. D into e to the power integration dx dxy is equal to, okay, qx into e to the power integration e into dx. Okay, so then if you solve this one, you will get e to the power integration dx into y equal integration qx e to the power integration dx. Okay, so that's the solution. Please try to understand these things. Okay, these things will be needed here. Now we have three transformations. Okay, we have three transformations. One is Fourier complex transformation. Okay, now we are going to talk about the PDE, solving PDE. Now we are going to talk about solving PDE. Okay, so please use this as a rule of thumb. If the range is minus infinity less than x less than plus infinity, use Fourier complex transform. Use Fourier complex transform. This is the rule. If minus infinity, if x is the range, x is the variable of which the range is minus infinity to plus infinity, then use the Fourier complex transform. Second situation, if u 0 comma y is known, okay, use Fourier sine transform, because if you remember in Fourier sine transform actually we have this term, that is why we are using the Fourier sine transform if we get this one. Okay, and here the range is x less than infinity. If it is minus infinity to plus infinity, actually you have to use the Fourier complex transform. The range is 0 to infinity, and if you know 0 to y, use 0y, then use Fourier sine transform. Third situation, if you know da by u over da by x, when x equals 0 is known, and the range is plus infinity, then use Fourier cosine transform. Okay, so these are the three rules. If the range of x is minus infinity to plus infinity, use the Fourier complex transform. If the range is 0 to infinity, and if you know u 0 comma y, then use Fourier sine transform. And the range is 0 to infinity, and if you know da by u over da by x when x equals 0, then use the Fourier cosine transform. These are the three things you should know. Okay, now let's quickly go through our handout and we will finish it before 4 o'clock. Right. So the first question, actually, we know that we did this one. Okay. So what we are doing here, let me use this one rather than writing it. It takes a lot of time. Okay. So this is actually the fourth derivative. This is actually the fourth derivative. So since it's a fourth, since it's the fourth derivative, so if you take the Fourier transform both sides, if you take the Fourier transform, what is the Fourier transform of? We know that da bar 4u over da bar x4. Okay. So what is the Fourier of variable is x. Therefore, that is equal to minus I omega to the power 4 into u bar. Okay, u bar. And this one is actually with respect to y. Therefore, that becomes this way. Okay, that becomes just d squared u bar by u over this one. So this is the differential equation we are getting. This is a differential. So if you write the auxiliary function, auxiliary equation of this one, we get e squared plus omega to the power 4 equals 0. Okay, so actually this is d minus I omega squared into e plus I omega squared. Okay, so complex solution. Actually, these are complex solution. Since it is complex solution, alpha is 0. Here, one solution is we have minus I omega. The other one is I omega squared. Therefore, we know that the complementary function is equal to u bar is equal to e to the power alpha is 0, no? So 0y a1 cos omega squared y a cos omega squared plus b sine omega squared y. So that is why we are having here. Okay, here minus is there, no? So here it is we have minus. No, yeah, don't minus. That is derivative. Here we are having this one. I'm sorry, not here. Here actually. So this is how we are getting this function. Then actually we are differentiating. Why we are differentiating? So always you differentiate this one. As a first step, you differentiate this one. So now if you differentiate this one, we are getting this one. Now actually we are going to use the initial condition. In order to use the initial condition only, we are having the differentiation here. In order to use the initial condition. Okay. So then we are taking the Fourier transform of the initial condition. So this is the Fourier transform. This is the initial condition. Look at the initial condition given. Da by u over da by y equals 0. And u equal fx when y equals 0. Actually, we have the function u bar. But the initial conditions are in u. Therefore, we want to convert this one. Look at here. I'm using this one. So initial condition, we have u, what? X comma 0. Okay, sorry. U, x comma 0 is equal to fx. Second one, da by u over da by y. When y equals 0, equals 0. We have these two initial conditions. Actually, we want to find we want to convert this into, we want to find actually u bar omega comma 0 is what. Similarly, we want da by u bar da by y when y equals 0 is what. These two we want. Actually, but the function we are having is the u bar function. Therefore, these are these initial conditions. Okay, these initial condition should be converted to this form, u bar omega y and da by u bar. That is why here we are taking the derivative. That is why here we are taking the derivative. And we are applying the definition of Fourier transform. So, since look at here, here the one variable is minus infinity to plus infinity. That is why we are using the Fourier complex transform. That is why we are using the Fourier complex transform. So then if you take this one minus infinity to plus infinity, e to the power I omega x da by u over da by y equals 0. This one. Okay. So this one is what actually, as I told you, this is what. This one is what? Since it's with respect to y, you can always take it out. So this becomes d over dy integration minus infinity to plus infinity. Okay, e to the power I omega x into u into dx. So this is what actually. This is nothing u bar. Therefore, da by da by u bar da by y equal 0. Why this is 0? Because we know that this part is 0. From the given information, from the given initial condition, this part is 0. When y equals 0, this part is 0. Therefore, right hand side is 0. Therefore, using this one, what we are doing, so we are substituting this one here. So when you substitute this one here, you are getting that uh, b equal to 0. You are getting that b equal to 0. Then your general solution reduced to a cos squared omega y. So now we want to find a. Already we found b. To find a, we are going to use the second initial condition. Second initial condition says what? E minus I omega x ux is equal to what? Function is what? U omega, sorry, ux comma 0 is equal to fx. So this is nothing but the Fourier transform of fx, Fourier transform of the function fx. So I am putting it as f bar omega. Therefore, using that one, I am finding y. So once I I am finding a. So my a is equal to f bar omega a. That is the Fourier transform of the function this one. Therefore, the solution is in this form. U bar is equal to f bar omega into cos omega squared y. Now, actually, we want the function u. So to get the function, we are taking the inverse Fourier transform and we are writing in this way. We are writing in this way because the function fx is unknown function. It's just the function fx. It is given as fx. So we don't know any information about fx. We don't have any information about fx. Therefore, we are just putting fx. Therefore, finally, we are giving the solution in the integral form. We are finally getting the integral form. Okay. So if you just want to write the steps, step one, okay, find the general, find u bar, okay, find u bar. Second one, differentiate u bar, because we are given this condition. We are given this condition. Therefore, we differentiate with respect to y. Second one, du bar over dy. Okay, you find this one. Third one, use initial conditions. There are two initial conditions, 1 and 2. Okay, fourth one, inverse Fourier transform. Then you will get the solution. Okay, you will get the solution. Now we'll move to the second example. Here, look at here. Actually, x is greater than 0. That means that we have x is greater than 0. Also, we are given ux comma 0 equal to fx. Ux comma 0 equal to fx. It's known. Actually, fx is not known. Fx is actually not known, but they have given us a function fx. So in that case, it is known. Therefore, what kind of transformation we want to use actually? Since x is greater than 0, x is greater than 0 mean what? X is between plus infinity and greater than 0. So we want to use Fourier sine transform. So we use the Fourier sine transform. Then we take the Fourier transform throughout the equation. So if you take the Fourier transform throughout the equation, so what is the thing you will get it here? Simply. This is the second derivative. Therefore, this will become minus I omega squared u bar plus, and this will become e squared u bar over ey squared equals 0. So actually I squared means minus 1. So we get the auxiliary equation becomes e squared minus omega squared, because this I squared is minus 1, minus into minus is yeah. So yeah, this becomes minus 1 omega u bar. So we have two solutions. One is omega and the other one is minus omega. Therefore, the solution, as you all expect, okay, you can write it as u bar equal to a into e to the power omega x plus b into e to the power minus omega x. A into omega x plus b into minus omega x. In this case, okay, in this case, actually, as I told you, if you let, okay, let me write this way. Say C and D, let's use C and D. Then if you take C equal a plus b by 2 and d equal a minus b by 2. Okay, actually you can write this as hyperbolic function. The same thing you can write it as hyperbolic one. So the solution becomes in this way. Solution becomes in this way. Okay. Now we have got the solution, but look at here. I'm using the notation S because I'm taking the sign transform. I'm taking the time. So you have to be careful with all these notations. Okay, because we are taking the sign transform, therefore you have to put S here. You have to put S here. So you have to be consistent with the notations. You have to be consistent with the notation. Now we have found this part. Okay, here also the first step is what? Finding u bar. Here we are earlier one we are using the complex transform. This time we are using the sign transform. That's all. That's the only difference. After that here, this is for Fourier complex transform. Fourier complex transform. Okay, for the Fourier sign transform, we first find this one. That is the first step. Find this one. Here, second one, you don't need to differentiate it because we don't have any differentiation here. If you look at the initial conditions, there is no initial condition with respect to derivative or related to derivative. Therefore, you don't need to take derivative. Here, actually, you had to take derivative because one of the initial condition is in terms of derivative. That is why you are having the derivative at this point. But here, you don't have such derivative here. You don't have any derivative here. Therefore, you don't need to we know these things. We know ux comma 0 as well as we know ux comma b. So these are the initial conditions we have, ux comma b. Okay. The second thing, u 0 comma y. We know these three things. Now what we want to do, we want to convert these to u bar x comma 0. Sorry, u bar not x, actually omega comma 0. U bar omega comma b and u bar 0 comma y. These are the three things you have to convert it. That is why here we are doing that. That is why. So first of all, what we are doing, we are converting this one, ux comma 0 sine omega x, because our function is this one. This is the initial condition. Now we are converting this. So then this is actually Fourier transform of Fourier sine transform of what? U x comma 0. So we are converting the first one. So that is equal to the function is given as fx. So here actually we are putting lambda because normally we put u no. So for an example, the Fourier transform of Fourier sine transform of fx, we are putting it as 0 to infinity f of u. Can you remember f of u into sine omega u? Okay, instead of putting u, because the function is u, we are putting another notation lambda. So this initial condition now transform to Fourier transform. Okay, transform to Fourier transformation. So therefore, Fourier sine transform of this initial condition is in this form. Similarly, the second one is what? This is actually Fourier sine transform of ux comma b. then that is what? Here actually we are given that this function is 0. Therefore, this part, this becomes 0. Therefore, u s omega b equal to 0. Okay. So look at here. We are transforming this given initial condition in terms of Fourier transform function. We are given this one, x comma 0, x comma b, and 0 comma y. So now we are converting this to this one. So to convert this one, what you have to do, you have to take the Fourier transform this one. Here Fourier sine transform. You have to take the Fourier sine transform. Here the function is 0, therefore right hand side will be 0. Here the function is fx, therefore right hand side will be that one. Okay, and then we are putting these two on. We are putting these two, and we are finding the value of a and b. So a becomes this one, and then yeah, we are putting this one. Actually, we are able to find a on, and here we are putting y equal b in this equation, and we are getting b equal this one. Okay, these are just simplifications. Please try to understand this one. Actually, here in this general solution, we have two constants a and b. In order to find this a and b only, we are doing all these works. We are doing what? We are converting the initial condition in terms of u bar. Okay, then we are trying to find the value of a and b. Okay, first what we are doing, we are putting y equals 0, and we are finding the value of a. And then we are putting y equal b, because we are given the initial condition when y equal 0 and y equal b. Okay, so then these are not actually initial condition, they are boundary condition, because y equals 0 and this is the initial condition. This is the initial condition. These are called boundary conditions, because boundary mean these are the boundaries of y, no? These are the boundaries of y, and these are the boundaries of y. Therefore, this is called the boundary condition, and this is called the initial condition. Now we are putting this one here, we are putting this one here, and we are finding the value of b. Now we are just substituting this one here. We are substituting this one here, and we are getting this one. Now, where we are using this one? Can anybody tell me where we are using this one? Where we are using this one? Where we are using this one? Can anybody tell me where we are using this one? Because when you take the Fourier transform of this one, can you remember this one? I think when you take the Fourier transform of this one, okay, Fourier transform of Fourier sine transform of da bar squared u over da by x squared is equal to what? Can anybody tell me? Omega u 0 comma y minus omega squared u bar. Okay, here only we are using that part. U 0 comma y is what? 0. So this part is 0. Therefore, this becomes minus omega squared u bar. Therefore, when you take the Fourier transform, of this one, okay, when you take the Fourier transform of this one, that becomes minus omega squared u bar. Okay, earlier I wrote wrong. Okay, I'm sorry for that. Actually, again I used the complex transform, I remember. So u bar my plus, and this is with respect to y, no? Therefore, that is nothing but e squared u bar over 0. So that is how we got this equation. Okay, that is how we got this equation. Do you understand now, students? How we got this equation? So actually, we are using this initial condition here. We are using this initial condition here, and this boundary condition in order to find a and b. Okay, so this initial condition we are using here in the transform. This boundary condition we are using in order to find the value of a and b. Do you understand? Tell me whether you understand this one or not. Okay. Okay. Please do this one again. Okay. Just close your books and try to do this one again and try to understand. Okay. Right. So then we get this answer. Here actually, it's a matter of changing the order of integration. Okay, because here we are asked to show the answer. This is the given answer. No? Given answers. There are some simplifications here. So similarly, you can use this one. Now, can you remember? Sine a minus b is equal to what? Sine a minus b is equal to, we have sine a cos b minus cos a sine b, or sine b cos a. Yeah? Similarly, you can do this for hyperbolic functions also. Sinh a minus b is equal to sinh a cos b minus cot a sinh b. Okay, most of the trigonometric identity are similar for hyperbolic also. Okay, except the sin squared theta plus cos squared theta is 1 in trigonometry. In hyperbolic, cos squared minus sin squared equal 1 minus. But most of the trigonometric identity like sin a minus b, sin a plus b is similar to sin a plus b and sin a minus b. We are doing that simplification here. Here actually we are doing we have two integration. Actually we have two integration. We are just changing the order of the integration. We're just changing the order of the integration. No problem. You can change the order of the integration. Okay. Say for an example, if you have two integration like this, let me write it here. Say you have two functions, 0 to infinity. Say fx integration minus infinity to plus infinity gy dy into dx. Okay, so this is equal to, you can change the order of integration, minus infinity to plus infinity, minus infinity to plus infinity. Then you can say 0 to infinity. You can say here gy, here fx, dx, dy. Okay, you can change the order of integration. You can change the order of integration. Similarly, here also it is shown that we are changing the integration. Okay, here look at the coefficient is 2 over pi because we are using the sign transform. Since we are using the sign transform, the coefficient is 2 over pi. And u bar is omega y into sine omega x and x y. Okay, right. Next question is the first order derivative. Look at the variable. Variable is 0 to infinity. And look at the initial condition. We are given da bar theta over da bar x. We are given da bar theta over da bar x when x equal 0 is non. Non. Meantime, the range is half range. That means that 0 to infinity. So what is the transformation we want to use? Can anybody tell me what is the transformation we want to use? If the range is 0 to infinity and da bar theta over da bar x is non, what is the thing we want to use? The Fourier cosine. We want to use the Fourier cosine. So we want to take the Fourier cosine. Here also our variable is our primary variable is x. Actually, in the previous handout, here this was plus. Please change this one. Okay, it should be minus. Huh? It should be minus. Okay, the work is correct. It should be minus. Okay, the one I sent, it was plus. Please change this as minus. Now we are going to take the Fourier transform. We are going to take the Fourier transform for this function. So Fourier cosine transform. So da bar theta over da bar t minus k is a constant or kappa is a constant, k into Fourier cosine transform of da bar square theta over da bar x square equals 0. Okay, so here because my t is the secondary variable, so I don't have any problem here. So I can write this as d theta over d theta bar, because I'm saying that the Fourier cosine transform of theta equal to theta bar c. C is important. Theta bar c over dt minus k into, here actually we know this one, but da bar theta over da bar x when x equals 0 minus omega squared theta bar c. Okay, omega squared theta bar c. So here, look at here, da bar theta over da bar x is equal to what? Minus mu. So that is minus mu. So this is minus mu. So this is minus into minus is, yeah, this is minus mu. Sorry, already there's a minus, no? Because if you look at the formula, look at here. That's that. Here, look at, there's already a minus. Already there's a minus. So so anyway, I write, sorry, yeah, actually we have, I show that one. Da bar t, sorry, we have da bar theta over da bar t minus k into da bar squared theta over da bar x squared equal to 0. So I'm taking the Fourier transform, cosine transform. So Fourier cosine transform of da bar theta over da bar t minus k into Fourier cosine transform of da bar squared theta over da bar x squared equal to 0. So this t is the secondary variable, so I don't have any problem. So I can write it as da bar theta bar c over dt minus k into, this one is actually, I know that da bar theta over da bar x minus when x equals 0 minus omega squared. Okay, this one is theta bar, omega squared theta bar. So this one becomes d theta bar c over dt minus k into, this one is given as minus mu. This one is given as minus mu. Therefore, minus into minus is plus. I will get minus k mu. Minus k mu. And minus into this one, I will get plus k omega squared theta bar c equals 0. So I will get the equation like d theta bar c over dt plus k omega squared theta bar c is equal to k mu. So this is first order differential equation. This one is the first order differential equation. So integrating factor of this one is e to the power k omega squared into dt, because the variable of this differential equation is t. So this is equal to e to the power k omega squared. Therefore, I can write it as d theta bar e to the power k omega squared t equal to, I have k mu e to the power k omega squared t into t. Okay, so this becomes theta bar e to the power k omega squared t is equal to, if I integrate this one with respect to t, I will get k mu over k omega squared into e to the power k omega square t plus c. So that is the one. So look at here. Yeah. So integrating factor is that one. And we are having this equation as I told you. And then we are getting this equation. So this is the point we are here now. Okay. So if you solve this equation, I mean, if you divide by this one, we get theta bar is equal to k cancel out. So we get mu over omega squared plus c times e to the power minus k omega squared. So this is theta bar. Now we want to find theta. We want to find theta. So we want to find c also. We want to find c also. For that one, we can use the initial conditions because initial condition is given here. Look at the initial condition. What are the initial conditions? Theta equals 0 when t equals 0. Theta equals 0 when t equals 0. That means that we know that theta x comma 0 equals 0. Therefore, we want to find out using this one, we want to find out theta bar omega 0. So for this one, we have to take the Fourier transform. We want to find this one, Fourier same transform. In every step, I want to put C, I'm sorry. Okay. So then how to find this one? So I want to take the Fourier transform, this one. So if I take the Fourier transform, Fourier cosine transform of this theta x comma 0 is equal to 0 to infinity theta x comma 0 into cos omega x into. So, but already this function is 0, therefore right hand side is 0 equal to this theta bar c. Therefore that is 0. So when t equals 0, when t equals 0, this one is 0. Therefore, I get, so I have the function this one, theta bar c is equal to, I have mu over omega squared plus c times e to the power minus k omega squared t. So if I use the initial condition theta bar omega comma 0 equals 0 implies as 0 equal mu over omega squared plus 0. Therefore, c becomes minus mu over omega squared. Therefore, my final solution, not the final solution, c is equal to, I get mu over omega squared minus, here also mu over omega squared into e to the power minus I omega minus I omega squared, sorry, minus k, no, k is also there, sorry, not I, minus k omega squared. So that is what I am having here. So I'm taking mu over omega squared out and I am having this one. Now I want to take the Fourier transform for this one because this is theta bar. So I'm taking the Fourier transform. So that becomes 2 over 5, 0 to infinity, this one. So we are giving the function in terms of integral. Okay. Do you understand this one? Tell me whether you understand this one. What about others? Only 77. What about others? Hello, are you there? Right. So today we completed this handout. And the next class we'll study finite Fourier transformation. Finite Fourier transformation. There also we'll talk about applications. So these are important. So please try to go through these three examples. There are three types of questions. One is using Fourier complex transform. Second one is Fourier sine transform. Third one is Fourier complex transform. So you must know the condition when to use the Fourier sine transform, when to use the Fourier cosine transform, when to use the Fourier complex transform. So if x is between minus infinity, sorry, plus infinity and minus infinity, the first one, then use Fourier transform. Second one, 0 less than x less than plus infinity, u x comma 0 non. Sorry. U 0 comma y non. I'm sorry. U 0 comma y. I'm sorry. Then use Fourier sine transform. Third one, 0x less than plus infinity, and you know da by u over da by x, when x equals 0, non, then you can use Fourier cosine transform. Okay. The second question, okay, okay, you can do now here, look at here in this handout, we have considered the general solution in this form, a cos omega y plus b sin omega y. So if somebody like you see omega x plus b minus omega x, then that is also fine. So as a homework, okay, please take the general solution in this form. Take the general solution. Rather than taking the general solution in this form, please take u bar s omega y as a e omega y plus e minus omega y, and try whether you can finally using the definition of hyperbolic and hyperbolic sine and hyperbolic coch, whether you can able to get this one. Okay, so please try it as a homework, and I will send a three problems. I will send three problems for this. One for Fourier transform, the other one for Fourier sine, the other one for Fourier cosine. Okay, so what you all have to do is, you just do it, you just do them, and send it to me. You just do them and send it to me. But what I'm going to do is I will do some changes. I will send the assignment. Okay, it's one of your assignment. Okay, so I will send three problems. I will slightly change the problem for different people. Okay, then because in order to refrain from copying, I will send that one. Okay. Also, I will send tutorial also. Please try to do this one. Next class, next week, I will try to finish all these integral, and then thereafter we'll finish the real analysis. Okay. Maybe in 1.5 class, I can finish the next handout. That is the last handout, and I will finish that one, and we can finish the integral transfer. Okay. So sometime, if possible, Saturday. Saturday is not possible. Anyway, next week, hopefully I will finish the integral transform, and thereafter we can have the real analysis. If possible, next week I will put more classes. I will put Monday also you all are free, no? Monday, Tuesday, maybe we can finish the integral transform, and Wednesday, Thursday, we can finish real analysis. Two classes, if we have, we can finish it. Okay. So that is what I am planning. After that, we can have some tutorial classes. Okay. Right. So with next week, hopefully I will finish the syllabus. Monday and Tuesday, I will put the integral transform. Wednesday and Thursday, I will put the real analysis, and then we can finish this whole thing. Okay. So that is what I am planning. And before that, I will send some question for this part. Okay. Because this is somewhat, somewhat complicated, because we are using complex transform, sine transform, and then we are using ordinary differential equation. We are dealing with the first order, second order. There are so many complications. So what you have to do is, I know it's difficult. There are different boundary conditions. There are different initial conditions. What you all have to do is, you just write the question on a piece of paper, and try to do it your own. And then if anywhere you stuck, just go through the handout and see where you stuck. Then you close it, and then you do it. Then again, you redo it. And that is how you can study. That is how you can do. Look at here, how we are using the initial condition to find this constant. That is the important part. Okay. The first one is now getting the writing the general solution is not that critical. Okay. Only the critical thing here is to find how to find the constant A and B. Okay. Right. So anyway, I will upload all the videos. I have already uploaded real analysis things. MATLAB is complete. And I have uploaded all the